Okay, 3.1, the definite integral. So on this, we're introducing the definite integral using some situations that maybe we've thought of before. All right, so on this first one, what we have is we have a car that is going at a constant rate, a constant speed or velocity of 40 miles per hour. And it travels along for 2 hours at this exact same velocity. So our goal is to figure out what was the distance traveled by this car. Okay, so shouldn't be too bad. As most of you know, that distance equals rate times time. Okay, so if distance equals rate times time, it's going at a constant rate, so it's going at 40 miles per hour, and it's going for 2 hours time. All right, so the hours get to cancel out. It looks like this car traveled 80 miles. All right, so not a big deal in this situation. Another way we would like to start thinking about the definite integral is with graphs like this, where it's going to be the area underneath a graph. So the area of a rectangle isn't that bad. Area of a rectangle could be length times width. Or in other circumstances, you may say base times height. But pretty basic as far as memorizing a formula to find the area of a rectangle. All right, let's go on to one more here where instead of going at a constant rate, we have a car that starts out and it's going to travel for 2 hours time, but it starts out at 0 miles per hour and steadily builds its speed over these 2 hours until it finally gets up to 40 miles per hour by the end of its trip. And yeah, we don't want to be behind this car, right? So the velocity is changing. It's not constant this time. So we would have a little bit of problems if we were thinking strictly in distance equals rate times time. Now we could fill in for the time, but the rate is changing, right? It's not going at a constant 40 miles per hour like our previous one was. Its rate, its velocity here is changing over time. So this is where thinking about these as the area underneath a curve, we've got our graph over on the left-hand side. We can calculate the area of that shape under the curve because the area this time is of a triangle, and its formula is 1/2 base times height. All right, these are the two main formulas that we want to sort of start getting down as we move through these problems. It's going to be an expectation. We can calculate the area of a rectangle and area of a triangle. So in this case, what I would say is we have traveled for 2 hours, so that's going to be the base of our triangle. And it gets all the way up, going from 0 to 40 miles per hour on the height. So in this case, we'll fill in, we'll say 1/2. Then we have 2 hours for our base, and our height was 40 miles per hour. Again, work with your units, multiplying and dividing by hours, so our units are going to be in miles when we get done. All right, this time it ends up we have 1/2 times 2, also multiplying and dividing by the same thing. Basically get to make a 1, so 2 over 2 makes 1, so we're going to be left with 40 miles total, which you may have been able to guess based on the previous one that we made it twice as far if we stayed at a constant 40 miles per hour. All right, we've got one more example that involves cars, so let's give this one a shot. So on this next one, last one on this video, we have two cars that are traveling along, A and B, represented in red and blue. So A is traveling at 80 feet per second at the beginning for the first 20 seconds, and then hits the brakes and slows down. B is traveling at 40 feet per second for 20 seconds, and then they both hit the brakes at the exact same time. So a few things we want to talk through here. First of all, on part A, we want to discuss, all right, after they hit the brakes, how long until their velocity got down to 0. So that's meaning we were at 80 feet per second for A, hits the brakes right there at 20 seconds, and we've stopped, right? Our velocity is down here at the x-axis at 0 at 40 seconds. Okay, so to do this first calculation, hit the brakes at 20 seconds, completely stopped at 40 seconds. that's going to be a quick subtraction, and A took 20 seconds to stop. It's going to be very similar on B. B hit the brakes here at 20 seconds. Velocity gets all the way down to 0 at 60 seconds. 60 minus 20 is going to mean it took 40 seconds to stop. All right, on part B, what we want to do is try to figure out who stopped first. All right, from the time the brakes were applied, which car traveled further. All right, so we want to calculate their distances for each one of these. Now on A, we can calculate that distance by figuring out what is the area of this triangle. Okay, so for A, the area of that triangle is going to be 1/2 base, which was 20 seconds, times height, which was 80 feet per second. A little bit of simplifying down here. Our seconds are going to go away, and we're going to have a distance of, I believe this works out to be 800 feet. Okay, something similar here for B, but B started hitting the brakes there at 20 seconds, ended at 60 seconds. So we need to calculate the area of the blue triangle for B. Again, it shouldn't be too bad. It's 1/2 base. This time it took 40 seconds to stop, so 40 seconds for our base. And they were traveling at 40 feet per second. So with a little bit of reducing down here, again, you can kind of say, well, the seconds get to cancel out. 1/2 times 40 times 40 also happens to work out to 800 feet. So both these triangles have the exact same area, and they cover the exact same distance to get stopped for each one of these cars, both A and B. So I hope this helps out. We want to start visualizing derivatives, definite integrals as being areas underneath the curve. All right, good luck.